Now, so we're going to move to a slightly different one. So we've been looking at, I don't know whether you guys can see that at the back. We've been looking at a beam like that where the load is applied here. So we have the support like this, and then we've been applying the load right up there. Usually you get that for a typical building like this, you get the beam running across like that, or beam running across like this. So what we want to do now is look at a different kind of loading where the loading is applied from here. And you get that when you support a structure like that. So this roof will have some vertical structure like this. And that vertical structure has to take the weight. And what we'll be looking at is what is the maximum weight you can put on a structure like that before it starts going this way. So our aim is to design a structure, find what is the maximum load you can put to prevent this going that way. So let's start. So I've introduced that. It's still based on design for strength because we are trying to find the maximum stress that structure can take before a particular failure mode will take place. And that failure mode is what is called that. So I've listed some of the things that we will be going through as we go on. And the same way as we've done the last few topics, we go through the basic derivation. It's not very long, and then we then start to use it. So let's move on. So we are familiar with the one on the left. So design for strength based on tensile stress. So that is intention. So all of you will have done that in your first year. So if you are pulling that way, that is the way that will fail. And what you normally do is that you find what is the maximum tension load you can put on it before this will take place. So you did your tensile test in your first year, did you or not? Yeah. So that's one. And the one that we've just been doing is something like this, where you have a beam with a load that apply in the transverse direction, and it will basically deflect. And we are trying to find what is the maximum load you can put in. Now we can find the corresponding maximum stress that will be developed in the beam and relate that to the maximum load we can put on the beam. Sometimes it's the deflection that is the main limiting design from what we've just done. If you have a maximum value of deflection that you do not want to exceed, you can work out what deflection your given load will give you and decide whether your given load is within the level that you want it to be. But what we'll be doing now is something like that. Now the load is now applied along the length of the beam. And what we'll be showing is the relationship between the length of the beam you have, what cross-section geometry you've got, because that will play a role, and the way you are supporting that beam. So we determine what is the load you can put on it. So let's start with that. So I brought here a typical simple case that's similar to the one I've just shown. So you have something like that. It's initially straight. You apply, you push it from the end. So I brought this because that is very easy to bend. If I use that, which is a bit shorter and also much bigger cross section, if I try to push it, it doesn't bend as easily as the first one that I showed. As we can see there, once that goes, then we are basically bending that. So there will be some magnitude of the bending moment that is resulting in that. And we'll be showing how we find that value. I've showed here some very unpleasant engineering design failure, which you'll be able to apply this. I'm going to explain this first. So has anybody seen that walking along a rail track before? So you don't want that to happen when the train that you are on is going past. And what is happening there is because of high temperature. So that is the temperature effect. So what happened is that the main track is on the floor, is bolted to the floor. If the temperature is very high, the track wants to move and expand. If it cannot expand, you develop an axial compression because the track wants to expand and you are trying to tell it not to do so. And if that compression force is very high, then you will end up with something like that. It's exactly the same as the one here. And this is very common in the North Sea. This will be a typical pipeline carrying oil or gas. So sometimes they are buried about 1 meter below the seabed. Because of the seabed, you have very high friction between the pipe and the seabed. So if the product that the pipe is trying to basically transport is very hot, then the pipe wants to increase in length, but because of the friction, so it cannot do so. And therefore, you develop an axial compressive force. And if that is very high, the only way the pipe can relieve that is to come out of the depth it's been buried or do this as well. And if that curvature is too large, just if I did that, if that curvature is too large, it's going to break here. And therefore, you lose whatever is in it. And the one for civil engineering, which I hope you're not the one that will design something like this. So it's the same, like I said, you have all these vertical columns, so which are supposed to take the weight of the roof. Therefore, if you don't do that correctly, if the weight is beyond the main capacity, then you get that, and the whole structure will just go down. And what we'll be doing now is to go through how do we determine what is the maximum load at which this will occur. What is the load at which this will occur? And we want to stay below that to make sure that we don't get something like that. Okay, yeah? Are we ready? So let's go. Right, so I will show the first slide and I'll do the derivation tomorrow because we don't have the time to do the rest. So let's go through this. So we want to look at, first I want to look at a case where both ends are pinned. Remember I said the load at which you get that type of failure mode depends on how you support your beam. Okay, so we look at a case where the two ends are pinned. What that means is that at the support, you can have free rotation, but no movement from the support. I would say pin. So no constraint on rotation. So that beam can rotate at the support, both here and at the top. But they are not supposed to move from the support because the role of the pin support is to keep them there, but the beam can rotate about that. So we've applied an axial load. So as you increase the axial load, initially you will get what we call uniform deformation, just like you are doing simple compression test. If I take that and I just apply that, if I squash that, that will just increase in length that way. It will increase in length that way. So, but as your load goes up, then at some point, depending on the length of the beam, then you will get something like that. And what we want to be able to show is what is that load. If I know the length and I know what type of cross section I've got, what load would that take place? So there are two aspects. One, which I will refer to as what is called short column, and I will explain that later. The short column will be something like this. So where this length here is compared to the size of this structure here. So if I take this, I will consider this as something that is very long, because this length here is very long relative to what I have at the top here. And we will see how we define that. If that is short, if it is a short column, what you will get is like a simple compression. If you are to do that, you will get the deflection will just do. Yeah, we'll just do that. And then if you have what is called slender column, which is the one that we're going to be focusing on, and we will see later on, hopefully tomorrow, what is the value of the transition between short and slender. So you will only get this type of failure mode if you have a slender one. So if I go back up here, I'm going to stop now because I will do the derivation tomorrow. If I have that, I know that is not too different from what we've been doing, because if I turn that this way, if you look at that, we now have a beam that has been bent, similar to the one that we've been doing. So I look at the magnitude of the deflection, what axial force, and what moment I've got at a given point, and I can write that down, which is what we've done before. I'll say I've got my magnitude of the deflection and the magnitude of the bending moment, and I will take it from there tomorrow, and then we'll use that. That is what we're going to use to find the maximum load we can put on that beam. So, okay, so I'll see you tomorrow.